Welcome back to Physics 141. We're going to start a new section in the course dealing with rotational dynamics. And this will occupy the next two chapters in the textbook. And you can see on the outline here that quite a few topics fall under this heading. As I mentioned in class, though, I encourage you to look for analogies between the rotational physics that we'll be studying in this section and the one-dimensional motion that we studied early on in the course. Many of the equations that we will use in this section are modified just a little bit from those one-dimensional equations that we studied back in the earlier part of the course. So, what I'd like to do today is begin with definitions of the angular position, velocity, and acceleration quantities that we will use to study rotational motion, and then look at a special case of rotational motion with constant angular acceleration, alpha. When a rigid body, which means an object whose shape stays the same, that doesn't deform, when this kind of an object rotates about a fixed axis, so that the rotation axis is fixed in space and is not moving, we can characterize the motion of a point on the object in a manner that's very similar to the way that we study the motion of a particle in one dimension. And you can see how this works by just looking at an arbitrary shaped object here, which is going to rotate about an axis perpendicular to the page that passes through the origin. And it's going to rotate counterclockwise. So we have the xy axis, the origin is where the axis passes through the plane, and let's just look at a piece on the object. And what we see is that no matter what shape the object is, every piece on the object, as long as the axis stays fixed, undergoes circular motion. And there are very, very simple relationships that relate the motion of an object around the circumference of a circle to the angle that it makes, in this case, with the positive x-axis. And the relationship between s and r and theta is a familiar one if you remember your geometry. So instead of keeping track of the position of the object using a distance like s, where s measures the arc length from the positive x-axis to where the object is located, we're going to use the angle theta. And the reason theta is such a good choice is that if an object is further away from the rotation axis, then the s value that it has at a particular point will be different than an object that's closer to the axis. All right? But the angle that those two objects make will be the same no matter what distance they are away from the rotation axis. And so that's why we prefer to use theta as our angular position rather than the linear position that we would have with a quantity like s. But there's a simple relation between s and theta. The linear position s is equal to r, the radial distance from the rotation axis, times theta. Now this equation, in order to be correct, has to have theta measured in radians. And so we will very rarely use degrees in order to talk about angles in this part of the course. We will almost always use radians because that's what this formula depends on. So the position of that object s is related to its angular position, theta. And in order to determine what we call the angular velocity, as the object rotates and as this point on the object undergoes this circular path, we can take the derivative of the linear position with respect to time. So ds dt would be the linear velocity of that object. V is equal to ds dt, which, if we just plug in s equals r theta, and remember that r is a constant, well, the r comes out in front, and ds dt is the same as r d theta dt. So remember, d theta by dt means the rate of change of angle with respect to time. And we give a simple symbol for that, omega, the Greek letter omega, lowercase omega. Now, please don't think of this as w. I hear people say that sometimes. That's not a w, it's omega. And so we will talk about it in that sense. we can go one step further and calculate the acceleration by taking the time derivative of the velocity. So the linear acceleration, a, is dv dt. Well, v is r omega. The r is again constant, so a is equal to r d omega dt. And we use the Greek letter alpha in order to denote d omega dt. So what we've got now is a connection between s, the linear position, and theta, the angular position, v, the linear velocity, and omega, the angular velocity, and a, the linear acceleration, with alpha, the angular acceleration. So, just to emphasize this again, we are defining an angular velocity, omega, which is going to be in radians per second. It's the rate of change of angle. And the angular acceleration, alpha, is defined as the rate of change of the angular speed. So this would be radians per second, or radians per second squared. And so, once again, in this part of the course, we're going to come up with expressions for many of the same physical quantities that we've encountered earlier. Things like velocity, acceleration, force, mass, kinetic energy, momentum. But these new quantities will be rotational versions of these linear quantities. And so this is what helps me remember the new equations that we're going to derive in this part of the course. Not to think of them as something completely brand new, but to relate them to things I already know. And I hope that thinking of it this way will help you as well to remember the equations of rotational dynamics and to understand what they mean. All right, now let's move on to rotational motion with constant angular acceleration. You'll remember earlier in the course we looked at kinematics, and we studied in particular the kinematic equations where we had constant linear acceleration. For example, the motion of a projectile near the Earth's surface. So this is going to be completely analogous, and we can start with the one-dimensional kinematic equations for constant acceleration motion and use them to derive the rotational versions of these equations. So imagine we have a rotating object like the one I showed in the previous slide, and any point on that object would undergo motion where v would be equal to v0 plus at. But we would prefer to write this down in terms of theta and omega and alpha. And it's easy to do that. We just have to substitute in that v is r omega and a is r alpha, where r is the distance of this point from the rotation axis. So when we make those substitutions, we get r omega equals r omega 0, where omega 0 is the initial angular velocity, and then we have r alpha times t. And look what happens. The r is in all three of those terms, so if we divide both sides by r, we just get omega equals omega 0 plus alpha t. Now notice how similar this is to the original equation that we had for linear motion, v equals v0 plus at. So omega is omega 0 plus alpha t. And if I just make the simple substitutions, I replace v with omega, and v0 with omega 0, and a with alpha, I can turn the linear equation into the rotational version of it. So that helps me remember what these equations are. And we can derive in a very similar way the other rotational kinematic equations, starting from the one-dimensional equations of kinematics for constant acceleration motion. What do we get? Here are the four one-dimensional motion equations that we studied with constant acceleration motion, and all we have to do, we did the first one already. We replace v with omega, and we replace a with alpha, and we get the rotational version. Here we replace x indicates linear position. Well, now we're going to replace that with theta. So theta minus theta 0 equals omega 0 t plus 1/2 alpha t squared. It looks just like this equation with the appropriate substitutions. One more time. What do we have here? V squared minus v0 squared. That's going to be omega squared minus omega 0 squared. And then on the right-hand side, 2 alpha times theta minus theta 0. And we could call this delta theta if we wanted to simplify it a little bit. And finally, this equation, which we don't use too often, but it has a rotational analog as well. Theta minus theta 0 is half omega 0 plus omega times t. So the equations on the right-hand side now, in the red boxes, are our new tools for studying rotational motion with constant acceleration. Let's do a quick example here. And you have several homework problems that are very similar to this kind of problem. An electric drill is operated at a rotational speed of 1500 RPM. And RPM is short for revolutions per minute. That is not the standard unit that is used to describe rotational velocity, but we'll see that it is. It is a rotational velocity with non-standard units. When the drill is turned off, it takes 4.5 seconds for it to stop spinning. And if you've ever used an electric drill, you're familiar with this. When you take your finger off the trigger, then it eventually slows down and stops, but it takes a few seconds for that to happen. What is the angular acceleration during this time, during the time the drill is slowing down, in radians per second squared? So we first follow our problem-solving strategy, the idea strategy, I. We want to identify and interpret the problem, and we can tell right away that this is a problem involving rotational kinematics. So let's put down those four equations that we had on the previous slide, and we will, in just a few minutes, figure out which one or ones we need to use to solve this problem. So D, right? Let's develop a plan here. Let's list the given quantities. Of course, I could draw a sketch here, but there's not really very much detail that I would be able to put in the sketch, so I'll skip that step for now. But we can make a list of what we're given. We're given the initial rotational speed that the drill has before we turn it off. So it's 1500 revolutions per minute. And we may have to do a unit conversion with this, but that's good enough for now. Of course, the time it takes to stop is 4.5 seconds. And it might seem like those are the only things given, but remember there's one other piece of information that's implied in this problem, and that is, think about it for a second, that is that the drill stops. And so at the end of the 4.5 seconds, omega, the angular velocity, is equal to 0. So that's important. We need to be able to interpret the problem and understand what information is being given to us. So these are the three given quantities, and now we want to look at the equations for constant angular acceleration motion and see which one will help us solve for alpha. Alpha is what we want to find, the angular acceleration alpha. So we need an equation that has these three quantities and alpha and nothing else. And sure enough, the first equation is exactly what we want. Omega, omega 0, alpha, and t. So we write that equation down. We want to solve for alpha, so we just do a little bit of algebra. Alpha is equal to omega minus omega 0 over t. Now we can evaluate. We can plug in the numerical values. Omega is equal to 0. Omega 0 is 1500 revolutions per minute. T is 4.5 seconds. But if we stopped at that point, then we would not have a standard unit. We'd have a mixture of minutes and seconds. So we don't want that. So the conversion factor, I'd like to get rid of minutes and get my answer in terms of seconds, or actually seconds squared here. So the conversion factor I need is 1 minute per 60 seconds, because then the minutes will cancel. And then I also need to convert revolutions to radians. And here is a quantity that takes just a moment to think of, but we will use this quite often whenever we're given information about the revolution, the number of revolutions of an object. So the conversion is that one revolution, one complete circular path, is equal to 2 pi radians. So since I have revolutions in the numerator, I want to use the conversion factor where the revolution is in the denominator. All right, so once I have the conversion factors in place, I get an answer, negative 34.9 radians per second squared. And check the units. The minutes cancel, the revolutions cancel, leaving radians over seconds times seconds. Right? So what can we say in assessing this answer? I don't know whether that number is a reasonable number. It's kind of hard to have good physical intuition about accelerations. But what we can do is realize that the units work out and that the answer is negative, which we should expect, right? Because the drill is slowing down. So an angular acceleration that's negative means the object's velocity is getting smaller. It is slowing down. And so that's a very simple problem using rotational kinematic equations. And again, you will have many opportunities to practice this on your homework. I'll see you in class.